Safe reinforcement learning through meta-learned instincts, from Djordje Grbic and Sebastian Risi. Reinforcement learning is a type of machine learning where an agent has to learn through interactions with an environment to maximize the sum of the rewards it collects during the lifetime. The agent observes the environment through state representations. Based on the representations, the agent generates an action with which it interacts with the environment. In deep reinforcement learning, the probability density distribution of agents' actions is defined by a policy model with a neural network. One way of training the neural network is by so-called policy gradient methods. Policy gradient methods, which we employ in our experiments, are a set of methods that optimize parameterized policies with respect to expected episode returns. The estimated gradient is then given to a gradient-based optimization method. Vanilla policy gradient methods can introduce catastrophically large updates on the policy, which can cause the network to deteriorate in its performance. To address this problem, the method called proximal policy optimization was introduced by Schulman et al., and it is one of the most commonly used policy gradient methods out there. This method limits the parameter updates to a trust region within the parameter space, where there is a small chance of performance deterioration. For that reason, we use proximal policy optimization in this paper. While current deep learning systems are good at learning a particular task, they still struggle to learn new tasks quickly. On the right-hand side, we can see that an agent is being trained to follow the green cylinder. On the left-hand side, we can see how many samples different policy gradient reinforcement learning methods need in order to solve these tasks, starting from randomly initialized neural network weights. The plot shows that training an agent to solve this relatively simple task requires the agent to sample several millions environment interactions. Naturally, the amount of samples needed to solve a task is prohibitive if we want a method that can learn online or when there is a constraint on training time. Meta-learning tries to address this challenge. The idea of meta-learning, or learning to learn, has been around since the late 1980s and is now a very active area of research. Meta-learning revolves around optimizing agents for efficiency at task adaptation instead of task adaptation itself. One very popular approach is model-agnostic meta-learning, introduced by Finn et al. In 2017. The focus of this method is finding a set of parameters to initialize the network with. The upper left image shows this concept. The initial parameters have to be located in the parameter space such that the agent can quickly find a set of parameters, here denoted with theta star 1 to 3, needed to solve a specific task. The method consists of two nested loops that can be seen on the lower left side of the slide. A task-specific inner loop and a task generalization outer loop. Each iteration of the inner loop samples a task from a task distribution and optimizes the parameters inherited from the outer loop to the sample task. The initialization parameters are reset to the original inherited value after each inner loop iteration. The outer loop then calculates the gradients from the old iteration parameters based on the loss of the updated parameters. The gradient is used to update the initialization parameters. MAML depends on propagating the gradient information from the inner optimization loop gradient update to the outer loop gradient update. This is very difficult to implement correctly. To alleviate this problem, Fernando et al. Published a paper in 2018 that uses the evolutionary algorithm in the outer loop as an optimization method. The outer loop contains a population of initialization weights that are evaluated in the inner loop on how well they can adapt to a set of specific tasks, giving a relatively small number of samples. The method is called meta-learning by Baldwin effect. We use this method as a basis for our paper. An important goal in reinforcement learning is to create agents that can quickly adapt to new goals, but at the same time avoid situations that might cause damage to themselves or the environments. One way agents learn is through exploration mechanisms, which are needed to discover new policies. However, in deep reinforcement learning, exploration is normally done by injecting noise in the action space. While performing well in many domains, this setup has the inherent risk that the noisy action lead agents to unsafe environment states. In this paper, we introduce a novel approach called Meta-Learned Instinctual Networks, MLIN, which allows agents to perform lifetime learning while avoiding hazardous states. The test domain in this paper is a 2D navigation task with 4 hazardous areas. The environment consists of an agent starting at the coordinate 0, 0. The goal of the agent is to learn how to reach one of 4 goals, represented by gray and red circles, only through the reward it receives at each time step. The agent does not know the location of the current goal and has to reach it only by adapting the policy through rewards. The reward is the negative distance of the current position to the goal state. The agent receives an additional penalty of -10 for each step it makes inside a hazard zone. An episode terminates if an agent gets within 0.01 units of the goal state, or the episode exceeds a maximum of 20 time steps. The hazardous areas in the environment test the agent's ability to adapt to new goal positions in a safe way. The agent's input is the position it currently occupies at the 8 rangefinders, which detect the proximity of the hazardous areas. The agent outputs a movement vector, delta x, delta y, from -0.1 to 0.1 range. The model architecture introduced in this paper consists of 2 neural network modules, a policy network and an instinctual network. A policy network is a neural network module that is trained to solve a specific task through reinforcement learning, while the instinctual network is kept fixed during task adaptation. The goal of the instinctual network is to override noisy actions of the policy network if the agent finds itself in a potentially dangerous situation. The specific architecture described here is suitable for reinforcement learning problems with continuous action spaces. The instinct network outputs 2 vectors, the instinctual deterministic action AI and the modulating vector S from 0 to 1 range. The policy network outputs a potentially stochastic action AP. AP gets modulated by element-wise multiplication with the suppression vector S. The instinctual action AI gets reverse modulated by the same suppression vector S. The final action is the sum of 2 modulated policy and instinct actions. Evolution determines the initial parameters P of a policy network together with hyperparameters H and the instinct network parameters I. During an evaluation that includes adaptation to different tasks, policy parameters P are updated through reinforcement learning, and performance is evaluated with the updated policy network parameters, returning a fitness for each task. The instinctual model remains unchanged throughout a lifetime of an agent. Modified policy parameters are not inherited by the next generation. The idea is for the instinctual network to learn how to prevent the policy from entering hazard zones on a much longer evolutionary scale, leaving to the policy network to adapt to a specific task within a lifetime. The whole training procedure runs 2 training loops, an evolutionary outer loop and a task adaptation inner loop. In the outer evolutionary loop, a simple genetic algorithm is optimizing the initial weights of the policy network, the weights of the instinctual network, and the learning rate used by the reinforcement learning algorithm in the inner loop. The weights of the instinctual module are only updated through mutations during the outer loop. In other words, instincts are fixed during agent's lifetime. Our specific implementation uses the proximal policy optimization algorithm for the policy gradient calculation in the inner loop. The PPO algorithm takes the action log probability sampled from the policy network, not the instinct modulated actions that interact with the environment. After the update, the algorithm samples the final trajectory where the policy network generates actions by taking the mean action of the policy-defined distribution. The cumulative episode reward is added to the exploration hazard violation punishments to get the task evaluation. The policy weights calculated with the gradient update are discarded after each task, i.e. we are performing a non-Lamarckian evolution. The final evaluation of the evolved parameters is the sum of task evaluations for each task visited in the inner loop. 4 goals in the 2D navigation task. The initial policy and the instinct parameters are optimized in the outer loop based on the inner loop evaluation value. On the left-hand side, we compare MLIN against a meta-learning version without an instinct network in a 2D navigation task with and without hazards. The curves show the average fitness among 5 runs for the hazard and non-hazard 2D navigation task. Shaded areas showed 1 standard deviation. We confirmed that the instinct and non-instinct modulated setup performs similarly in the environment without the hazards. We see that the presence of hazard zones, the instinct module helps the agent outperform the control setup. On the right-hand side, the green lines show the exploration trajectories, while the purple line is the deterministic trajectory of the model after the first gradient update. The agent is able to learn to navigate to the 4 target goals during its lifetime while avoiding hazards. If we take the best trained models and repeat the inner loop over 20 times, we see that our approach maintains high fitness and low hazard violations, while the control gets stuck in a local optimum where it minimizes the hazard violation while having suboptimal goal reaching capability. The exploration plot on the right-hand side shows how much instinct contributes to the final action. The redder the step, the more it was influenced by the instinct and the less by the stochastic action from the policy network. As we can see on the plot, the areas where the instinct has the highest contribution in the final action are exactly around critical areas around the hazard zones. The purple line at the end shows the deterministic non-exploratory trajectory after the update based on the exploratory trajectories. On the left-hand side, we can see the exploration trajectories of a train setup seen on the previous slide, only with the instinct module removed. The exploration is done only with the optimized initial weights of the plastic policy. We can see that the plastic policy causes many safety violation steps over the hazard zones. On the right-hand side, we can see the exploration trajectories of the train setup seen on the previous slide with the initial weights of the policy network replaced with a randomly initialized set of weights. We see that even in this case, the instinct provides limited protection when exploring around the hazard zones. Safety in deep reinforcement learning is a prerequisite condition for someday applying these methods in the real world. Here we demonstrate that a slowly changing instinct component that can regulate the noisy actions of a policy network during the exploration can avoid hazardous areas while consistently adapting to specific goals in a simple navigation environment. Interestingly, the solution the meta-trained model finds is not to completely suppress the actions from the policy network, but to redirect them by changing the direction of the average instinctual action. An interesting future research direction is to further explore the extent of the Baldwin effect, proposed by Hinton and Nolan in 1987, in MLIN, which could explain some of its superior performance. Adapting the setup presented here to more challenging tasks is an important next step. One such environment is the recently published OpenAI Safety Gym benchmark by Ray et al. From the last year, which contains multiple different tasks such as reaching goals, pushing objects towards goals, and avoiding static and moving dangers during learning. And with this, I thank you for your attention, and I'm open for your questions.